All right, this is the last thing we're going to do in chapter 29. It's called Ampere's law, which is kind of part of one of Maxwell's equations. Not the whole thing, but it's part of it. Anyway, so Ampere's law looks terrible. It looks as bad as Gauss's law, but it's actually even better. It's not even as complicated as Gauss's law. It just looks terrible. So it's just this horrible looking integral on the left is equal to a constant times I enclosed. This is the current which is enclosed inside something. So the left-hand side of this nasty looking integral, inside we have a dot product of a magnetic field with some length vector, where a dot product is always going to be the magnitude of our two vectors times the cosine of the angle between them. That's what vector dot products mean. And what this really says is it's talking about the magnetic field along some closed loop. So ds has to be a closed loop, not just some length, but a length of some closed path, some closed loop. So it can't just be a length ds. It has to be something that closes in on itself. So we're always going to choose, if we choose some closed loop, some closed path, where again, the magnetic field is constant. If we choose that, the magnetic field is constant, and the angle between these things is constant, then our crazy looking integral just becomes this. And in fact, almost all the time for us, the angle between the length and the magnetic field is going to be 0. And so we just end up with B times the length of our loop. That's what our crazy looking integral B ds is always going to be equal to. And I think in almost all of our situations, the actual length is just going to be the circumference of a circle. Our loop is going to be a circle, like here. So here's our Amperian loop. It's got a length, which is 2 pi r, and the magnetic field and the ds vector are aligned, and so our theta is 0. And so this integral just becomes this. So don't freak out by seeing this nasty looking thing. It just means this, B times the circumference of a circle. And I think the only one that I have you do of the practice problems that uses Ampere's law is number 43. So number 43 shows us a wire. This is actually, this whole shaded region is the wire. So we're looking inside the wire. And this wire has a radius, little a, which is 2 centimeters. And it's carrying a current of 170 amps through this wire. It might be the current's going in, maybe the current's going out. All we care about is the magnitude of the magnetic field, so we're less concerned whether or not the magnetic field is going this way or the other way around this wire. And we're going to use Ampere's law that says that this thing is equal to the constant times the current, which is enclosed, to figure out the magnitude of the magnetic field. So we're going to get magnetic field out of this. And remember that this is always going to be basically this for our purposes. So it actually has this, part A says start at r equals 0 and then 1 centimeter and 2 centimeters first, but we're going to go backwards. So we're going to do the last part first. We're going to start at an r of equal to 4 centimeters. This is outside the wire. So here's my actual Amperian loop for this situation. This is at a radius of 4 centimeters. If I'm out here, then the current which is enclosed is the entire current. It's 170 amps. And so my equation, which says this nasty thing, which really means this thing, has to equal mu naught I enclosed. That means the magnitude of the magnetic field is just mu naught I enclosed over 2 pi r, where my r is 0.04 meters. So let me erase this and we'll actually go through and do it ourselves. So here I'll say my mu naught, 170 amps over 2 pi and 0.04 meters. And if I do that math, times 170 divided by 0.04, I get that 8.5 times 10 to the negative 4 Teslas. So my magnetic field out there at this place, and everywhere along this place, my magnetic field is constant, right? At some equal distance r away, the magnetic field will be constant. In fact, this is the equation for the magnetic field strength at the center of a circular loop, right? Or some distance away from this magnetic field being produced by a wire at some distance r away that I presented in the last lecture. All right, part C says, what if you're at the radius of the circle? What if you're at the radius of the wire? So here's my Amperian loop for this one. I'm right on the edge. Well, the eye that's enclosed is still just barely, but it's all the current is enclosed at that location. So again, my crazy integral just equals this, mu naught I enclosed. So my magnetic field strength is mu naught 170 over 2 par. But now I'm only at 2 centimeters away. So this is a stronger magnetic field. It's twice as strong. All right, this is actually the hardest one. Part B, it says we're at an R where we're halfway out. We're inside our loop. So here's my Amperian loop now. I love that term, Amperian loop. So I have to figure out how much current is enclosed here. It's not all of the current. The current which is enclosed. So first I'm going to say, all right, there's a total of 170 amps of current. But it's spread out over this whole area. It's spread out over this whole area, which is pi a squared, right? It's pi a squared. But the area that I actually care about, the area that's enclosed, is just the part which is in here, which is pi a over 2 squared. So the amount of current which is enclosed is actually, this is a little ugly, a over 2 squared over a squared. Right? These pi's go away, and in fact the a's go away, and I'm just left with 1 over 2 squared, which is 1/4. So the amount of current which is enclosed is just 1/4 of the total current. That's the hardest part of this problem, because then once again we're left with the magnetic field times 2 pi r is mu naught I enclosed. So the magnetic field strength is mu naught, and now our current which is enclosed is 42.5 amps over 2 pi, and then we're at an R of 1 centimeter. Which has, so we have a magnetic field strength of 8.5 times 10 to the negative 4 Teslas. Actually, it's very similar to the magnetic field strength that we had out at 4 centimeters. And then here, if part A is the easiest one, if R is equal to 0, then there's no current which is enclosed, and our magnetic field strength is 0. And that's really all I expect you to be able to do with Ampere's law. is just basically say b 2 pi r is mu naught that I enclosed. That's all for 28 and 29. They're a little longer this week than they normally would be for this material because this is not particularly complicated. But again, I'm not going to have in-person or Zoom classes on Wednesday or Friday, only on Monday. It's possible that next weekend I might be able to schedule something for review for the quiz, but we'll just have to see. Hopefully this will prepare you for the quiz enough. All right.